Section 2.2, set operations. So the union of two sets, A and B, denoted A, U-like symbol, is the set that contains elements that are either in A or B or both. In the set builder notation there, you'll notice that the criteria is that X is an element in A or X is an element in B. The OR symbol is that V-looking shape. So notice the similarity between the union symbol and the OR symbol. That'll help you memorize it. As a Venn diagram, looks like this. In blue there is the union A and B. Are both completely shaded, all the elements. Example, if A is ACEFG and B is the set BCH, then the union is any element that is in either of them, that is A, B, C, E, F, G, H. If C is the set of CS majors and M is the set of math majors, then the union of these sets are the set of students who are either majoring in math or computer science. The intersection is similar. The intersection of sets A and B, denoted A intersects symbol B, is the set that contains elements that are in both A and B. Again, in set builder notation, notice the similarity between the AND symbol and the intersection symbol for sets. Visually, again, in blue is that intersection. And you'll see it represented by the intersection of those two circles in the Venn diagram. For example 2 on this page, we're looking for an element that is in both A and B. The only element that is in both is C. And for our verbal example, if C is computer science majors, M is math majors, what is the intersection? Well, those would be the students who are double majors. That is, they're majoring in both math and computer science. We call two sets disjoint if their intersection is the empty set. You'll notice that visually, this means the two circles are disjointed. They don't overlap. For example, if A is the set ACEFG, but now B is the set BDH, these two sets have nothing in common. So we'd say their intersection is the empty set. We could say A and B are disjoint. Let's look at an interesting example. How do you calculate the cardinality of the union? And I'm going to go into depth in this example because it shows a common proof strategy called inclusion-exclusion. So we're going to count the elements that are in the union. So I might begin by first counting the elements that are in union A. Let me go ahead and shade that. I count those elements. There are 5 of those, A, C, E, F, and G. Next, I go through and I count the elements that are in B. There are 3 of those, B, C, H. Now the problem here is that you'll see right there in the intersection, it's been shaded both blue and purple. So anything that's been in the intersection, in this case, the element C, has been overcount. It's been counted twice. So what we have to do is we have to get clever and we have to subtract out 1 copy of the intersection. So now it'll just be shaded the 1 color. However, the formula holds. So the cardinality for the union is actually cardinality of A plus cardinality of B minus the cardinality of the intersection. And this scales up. Right, if we had 3 sets, we'd have to continue to use a strategy such as this, right? Overcount, correct. Overcount, correct. Include, exclude, include, exclude. The difference of sets A and B, denoted A minus B, is the set that contains the elements that are in A but not in B. The tricky part with the difference of sets is that the order here is really important. Notice from the definition, it contains elements that are in A. So at the end of all this, where we take A and we subtract B, we should be ending with elements that are in A. So it's also called the complement of B with respect to A, right? It's all the elements that are not in B that are in A. We call that the complement. You can denote this as A slash B. Again, don't. This is not the difference you're used to in algebra. This is not any sort of division that you're used to. We're talking about sets. We're using some of the same symbols, but the operations mean something different here. So the set builder notation, again, is a great way to dive into how to think about this. It's the elements where the elements are in A, but not in B. So shaded in blue here is all of A, but now I need to subtract out any elements that are also a part of B. So this is what I end up with, that little moon shape. I think the set builder notation, really focus on that for complements. The leftover there, that whenever you get done with it, elements in A. So always think of A minus B as starting with all the things in A, and you just take away elements that are in B. So if we want to start with A being the set ACEFG and B being the set BCH, we start with all those elements in A. We take away any of them that are also in B. In this case, just the C. So the difference, A minus B, turns out to be AEFG. So if we have C be the same set it's been for computer science majors, M is math majors, then whenever we do C minus M, we actually get SIB students who are CS majors. So they have to be CS majors, but they cannot be math majors. Let the complements, let U be the universal set. The complement of the set A, denoted A with the bar on top, is the set universe minus A. So it's this all possible objects, the universe, minus anything that is in A. So if this is our original looking Venn diagram, right, we have U, our universe, that rectangle, A is what's in blue. Then whenever we complement it, we get this. A bar is now everything that is in the complement and shaded there in blue. So if A is the same A we've been dealing with all along, A, C, E, F, G, and the universe is the set of English letters, then the complement is going to be all the letters that are not A, C, E, F, and G. What is the complement of our set C there? The complement of the computer science majors? That's anyone who's not a computer science major. We get a big long list here. They're in your note of set identities. These identities function very similar to your propositional logic identities. Keep an eye again on those De Morgan's laws for set identities. Let's talk about how you would show one of these. How do you prove one of these identities is true? So let's show that A union B complement is the same as the intersection of the complements. So we're going to show you two ways to do this. The first is this kind of general technique, sort of like inclusion exclusion I mentioned last time. This technique might just be useful in other cases for you. So we're going to show that they have to be subsets of each other. If they're subsets of each other, then they have to be the same thing, because I'm going to show elements in one are elements in the other, and vice versa. So let's start by showing that elements in the complement of the union have to be in the intersection of the complements. So just hang on here. It's going to be a lot of definition application. It's not terribly exciting, but I'm going to trace an element. Let's call that element X. So X is any element that you want from the complement of the union. By definition of the complement, then, it is not an element that is in the union. By definition of the union, it is not an element in A and it's not an element in B. Typo there. Oh, sorry. Looking at the wrong spot. By definition of the complement, so the complement of A and B, we get that if X is not an element of A, it is an element of the complement. So by definition of the complement, X is an element in A complement and it's an element in B complement. Well, if it's an element in both of those, then it's an element in the intersection by definition of the intersection. So we've traced an element and said, hey, if you are in fact an element that is in the complement of the union, you must be an element that is in the intersection of the complements. Now, the next part that we need is that doesn't mean we have all of the elements that are in the intersection. There could be stuff unaccounted for. So we have to do this the other way as well. Is it true that if you're an element in the intersection of the complements, you must be an element then that is in the complement of the union? So we're going to use the same trick. We're going to trace a generic element all the way through. Let's pick any element we want, call it X. By definition of the intersection, if X is in A, or the complement of A, sorry, if X is an element that is in the intersection of A complement B complement, then X must be an element that is in A complement and in B complement. That means, by definition of the complement, that element cannot be an element in A and cannot be an element in B. Use the negation symbol, right, by definition of not an element. Here's the tricky one. Apply De Morgan's then. Right, this is, don't be thrown off here. This is quote unquote De Morgan's in reverse from the way you have it listed on your sheet, but equals is equals. So we're going the other way. We're quote unquote pulling that negation out. So now we have that it is not the case that X is an element in A or X is an element in B. X is an element in A or X is an element in B is the definition of the union. Still have that negation symbol on the outside. So we can conclude then by the definition of the complement that X is not an element in A union B. So every element in the intersection of the complements must be an element that is in the complement of the union. So we've shown that they are subsets of each other, so they must be identical. The other way to do this, and this is the more straightforward way, is to use set builder notation. So what are the restrictions on being an element in the complement of the union? It means you are not an element in the union by definition of the complement. Pull that negation out by definition of not an element. By definition of the union, you can change that union of A and B to be X is an element of A or X is an element of B. Apply De Morgan's. Use the definition of not an element. By definition of complement. By definition of intersection. Sorry, I went a little faster this time. It's applying a lot of the same tricks we used on the last one. But now you can see that the set notation literally says, hey, you're only an element of A union B if you're an element of the intersection of the complements. Let's talk about generalized unions and intersections. Obviously, our Venn diagrams have their limits. They don't expand upwards very well, but the union of A, B, and C, I'm going to shade that in blue, looks like this. The intersection of A, B, and C, shade that in purple, looks like this. So we have a way to compress that symbol, to compress that idea. So if you want to union a bunch of sets, in this case A1 through AN, you can write it as union of AIs, where I's go from 1 to N. The intersection works the same way. We can talk about the intersection of a sub i's. Well, what are the i's? I's are numbers 1 to n. So let's apply this to an example. Suppose the AIs are constructed like this. AI is the numbers 2 through I, where I is 1, 2, 3, so forth and so on. So I want to look at the union of AIs from 1 to n. So A1 through AN. What does that look like? How do I get started on this? And the truth is that whenever you get stuck on a problem like this, I can't stress enough how much it's worth to just grab another sheet of paper and just start exploring. What do these AIs really look like? So I'm going to take the time to write a couple of them down. A1 is just the set containing 1. A2 is the set containing 1 and 2. A3 is the set containing 1, 2, 3. So forth and so on. So forth and so on. So when I go to now write the union of them, I can write it with at least a little more detail. So what's it going to look like if I take the union of the set 1, union with set 1, 2, union with set 1, 2, 3, union with so forth and so on to a union with the set 1, 2, 3 through n. This is just the set 1, 2, 3 through n. What is the set 1, 2, 3 through n called? This is the set AN. Let's try the next one. What if I intersect the sets AI, where I goes from 1 to n? Again, let's write it with a little more detail. Intersect set containing 1. Intersect set containing 1, 2. Intersect with 1, 2, 3. Intersect with 1, 2, 3, 4. All the way through 1, 2, 3 through n. Here we get reduced down. What do they all have in common? They only have the element 1 in common. We have a fancier name for the set that contains just the element 1. This is the element A1. Sorry, said the element, I think. The set A sub 1. Keep going. What's it look like if I take the union of A sub i's from 1 to infinity? This one requires some thought. What's that going to go off to? Well, it doesn't stop at the set that contains 1 through n, because then it goes on to the next, and then the next, and then the next. This will be the set of positive integers, right? It will keep going on up to infinity until it's the set of positive integers. What about the intersection? What about intersect the A1 through A2 all the way through to infinity? Well, it doesn't matter. We can see that happening from the second line there. The only element they're all going to have in common, 1. So the infinite intersection of AIs is A1. One kind of small last thing we're going to go over here is the computer representation of these sets. So the key here is to assume that the universal set, that the universe that we're looking at is finite. And in this case has cardinality n. So we assign an order to the sets. They don't have to have, I'm sorry, an order to the elements. They don't have to have a natural ordering is what they're called. We just need to put them in an order to represent it. Right, if I was going to put the citrus fruits in here, they don't have a natural ordering, right? I could order them by size. I could order them by growth rate, right? Or I don't know, any other number of things, right? But the point is I have to put them in some order and say this is the first fruit. So I use a bit string length n to represent a subset A of that universe. The ith bit is a 1 if A sub I is in that subset A. It's a 0 if it's not. So if I let U be the set of letters from A through J, so the first 10 letters, I'm going to let A be the set A, C, E, F, G, and B be the set B, C, H. Then this is what the representation of them will look like. Like before, I can do, now that I have them in this representation, I can do some of these set operations pretty quickly. The complement just swaps the zeros to ones and vice versa. So the complement of A is really easy to find. If I had a 1 in the ith spot, I make it a 0 in the ith spot. Translating this back is also pretty easy. I can see that the ones are in spots B, D, H, I, J, which are the elements in the complement. They're the elements that are not in A, C, E, F, G, the set A. I can do a union. So that it gets a 1 if there's a 1 in either A or B above it. I can do an intersection. That's an and. So I'm going to put a 1 in the intersection if there's a 1 in both A and B with this representation. And that will do it for section 2.2.